Let us continue our discussion of section 1.3, mathematical induction. Last time we discussed examples from 1 to 4. Let us take a look at example 5. Again, we want to use math induction to prove this identity. So here's what we do. Step 1, show that this identity is true for n is equal to 1. If n is equal to 1, the left-hand side is just 1 over 1 times 3. Why? Indeed, if you replace n by 1 here and here, this expression becomes 2 times 1 minus 1, which is 1. This expression becomes 2 times 1 plus 1, which is 3. So, if n is equal to 1, the bottom here is 1 times 3. Therefore, if n is equal to 1, the left-hand side consists of just one term, this term. If n is equal to 1, the right-hand side is 1 divided by 2 times 1 plus 1, which is 1 over 3. A left-hand side is equal to right-hand side. We are done with step 1. Now, step 2. Suppose this is true for some n is equal to k, where k is greater or equal to 1. That is this. So, in order to jump from here to here, we just replace n by k. That's it. And now, hard part is step 3. Now we want to prove that this is true for n is equal to k plus 1. So, step 1, we replace n here, 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 and here by k plus 1. Done. Done. And again, for convenience, let us write down the previous term. We will need it in a moment in order to prove this, because we will use step 2. So let us first simplify the left-hand side. First we copy the left-hand side, then we expand parentheses. 2 times k plus 1 is 2k plus 2. Same as here. Then 2 minus 1 is 1, 2 plus 1 is 3. So this is the left-hand side. Note that by step 2, the sum of these terms, which is exactly what is written here, is equal to k divided by 2k plus 1. So we replace this by k divided by 2k plus 1. We leave the last term without change. Once again, what we see in front of us here is the simplified left-hand side. But left-hand side should be equal to the right-hand side. So again, here we put question mark and the right-hand side. We still have to prove that this is identically equal to this. How do we prove it? First, let us copy it, and then we expand parentheses first here. 2k plus 2 plus 1 is 2k plus 3. Then, in order to come up with a common denominator, let us multiply top and bottom here by 2k plus 3. After that, we add up tops. Done. Then we multiply the left-hand side and the right-hand side by 2k plus 3. 2k plus 3 is gone on the right. 2k plus 3 is gone on the left. Then we multiply the left-hand side and the right-hand side by 2k plus 1. Done. Lastly, let us expand parentheses over here and over here. Done. Since 3k is equal to k plus 2k, the left-hand side is identically equal to the right-hand side. Therefore, question mark is gone. Lastly, we put arrows upwards. Once again, strictly speaking, we cannot deduce anything from this because we are supposed to prove it. However, since this is obviously true, this by algebra implies this, which implies this, which implies this, and so on, which implies this. We are completely done. Next example. Example 6. Prove this identity. Please take a look at this. N is greater or equal to 2. Since n is greater or equal to 2, in step 1, we show that this is true for n is equal to 2, not for n is equal to 1. If n is equal to 2, this term becomes 1 times 2. Therefore, on the left-hand side, if n is equal to 2, we have just one term, 1 times 2. It's exactly what is written here. Then we replace n here, here, and here by 2. Done. And one can easily check that the left-hand side, which is 2, is equal to the right-hand side, which is 2 times 1 times 3, 6, divided by 3, 2. We are done with step number 1. Step number 2. Suppose this is true for some integer n is equal to k, where k is greater or equal to 2, because here we have 2. That is this. Step 3, we prove this for n is equal to k plus 1. If n is equal to k plus 1, the right-hand side becomes this. This term becomes k times k plus 1, and the previous term is k minus 1 times k. How do we prove it? We copy the left-hand side. Done. Note that by step 2, this, which is over here, is equal to k times k minus 1 times k plus 1 over 3. Done. We add the last term. Done. What we see in front of us here is the left-hand side. But the left-hand side should be equal to the right-hand side. So still question mark. We have to prove that this is equal to this. How do we do that? Copy it over here. Multiply the left-hand side and the right-hand side by 3. 3 is gone here, 3 is gone here, and now we get 3 over here. We expand parentheses. Done. We expand parentheses. Done. We expand parentheses. Done. And then we expand parentheses over here. Here's the result. And over here. Here is the result. Lastly, we collect like terms. K squared minus k squared, 0, plus 3k squared, 3k squared. Negative k plus 3k is 2k. Over here, 2k squared plus k squared is 3k squared. Obviously, this is true. This implies this, which implies this, and so on, which implies this. Next type of problems. Problems about divisibility. This vertical bar means divides. Prove that 3 divides 4 to nth power minus 1 for any integer n greater or equal to 0. Now, you may ask my question, what does it mean, 3 divides? 3 divides 4 to nth power minus 1 means the following. 4 to nth power minus 1 can be written as 3 times k, where k is an integer. So, we want to prove that 3 divides 4 to nth power minus 1 for any integer n greater or equal to 0. Step 1. Show that this is true for n is equal to 0. Note that if n is equal to 0, 4 to 0 power is 1, 1 minus 1 is 0, 3 does divide 0, because 0 can be written as 3 times integer. 0 is 3 times 0. Now, step 2. Suppose 3 divides 4 to nth power minus 1 for some integer n is equal to k, where k is greater or equal to 0. That is, 3 divides this. Prove that 3 divides 4 to nth power minus 1 for n is equal to k plus 1. That is this. Here's how we do it. We start with this expression. It's over here. Let me remind you, in previous examples, one of the goals was to extract step 2 term from step 3 term. It's exactly what we did in all previous examples. This is step 3 term. This is step 2 term. We replace step 2 term by this. But how can we do it here? Here's an idea. Note that 4 to k plus 1 can be written as 4 times 4 to k's power. Note that 4 is 3 plus 1. Now let us expand parentheses. 3 times 4 to k's power. It's over here. 1 times 4 to k's power is just 4 to k's power. And now, this term is obviously divisible by 3 because it is of the form 3 times integer. This term is divisible by 3 by step 2. Since this is divisible by 3 and this is divisible by 3, the whole thing is divisible by 3, and therefore this is divisible by 3. We are done. Folks, think about questions here.
I have a question.
Yes.
So do we always have to, like for induction, do we always have to use step 2?
Yes, that's the whole point about induction. We can prove that this is divisible by 3 in several different ways. Here we want to use induction. And one of the main ideas, probably the main idea of induction, is the following. In order to come up with step 3, we use step 2.
Okay.
Next. We want to prove that 3 to the power 2n minus 1 is divisible by 8 for any integer n greater or equal to 0. Step 1. Show that this is true for n is equal to 0. If n is equal to 0, 1 minus 1 is 0. 8 does divide 0. Step 2. Suppose this is true for some n is equal to k, where k is greater or equal to 0. That is this. Step 3. We want to prove that 8 divides this if n is equal to k plus 1. We want to prove this. We start with this expression. It's over here. Let us expand parentheses first. Done. By algebra, 3 to the power 2k plus 2 is identically equal to the following. 3 to 2k times 3 squared, which is 9. 9 can be rewritten as 8 plus 1. We expand parentheses, we get this. Term number 1 is divisible by 8 because it is of the form 8 times integer. Term number 2 is divisible by 8 thanks to step 2. Since this is divisible by 8 and this is divisible by 8, the whole thing is divisible by 8. Since this is identically equal to this is divisible by 8.
I have a question. For the second term, the 3 to the 2k minus 1, we can make that assumption because of step 2?
Yes, that's the whole point. You see, it's written step 2. By step 2, this is divisible by 8. That's the whole point.
But how do we know that is true?
Because here we say suppose this is true for n is equal to k.
Okay.
Can we suppose it? Yes, thanks to step 1. But step 1, indeed, there exists an integer such that this is divisible by 8. For example, 0. Thanks to step 1, we can suppose that this is true for some, not for any. For some integer n is equal to k, where k is greater or equal to 0. Thanks to 1, we can suppose this. And now, thanks to combination of step 2 and step 3, from n is equal to k, we can jump to n is equal to k plus 1. And therefore, we can jump from case n is equal to k plus 1 to case n is equal to k plus 2. And therefore, we can jump from case n is equal to k plus 2 to case n is equal to k plus 3, and so on. This proves the whole thing. This is why, if we put together step 1, step 2, step 3, we conclude that 8 divides this for any integer n greater or equal to 0. Does this make sense?
Yes, that's perfect. Thank you.
Next, prove that 3 divides n cubed minus n for any integer n. There is a difference between example 9 and all previous examples. In all previous examples, there was a lowest term. Here, a lowest term is 0. Here, lowest term is 0. Here, a lowest term is 2. Here, a lowest term is 1, and so on. Note that there is no lowest term here. We want to prove this for any integer n, positive or negative. So what do we do? Think about the following. In step 1, let us show that this is true for some value of n of our choice. Compare with, say, example 8. In example 8, we do not have any choice. In step 1, we have to prove it for n is equal to 0. Over here, since we have to prove it for any integer n, we can put instead of 0 basically any number. But the easiest case is when n is equal to 0. Obviously, 3 divides 0 cubed minus 0. Step 2 is basically same as before. We just replace n by k. But then please take a look at step 3. In all previous examples, step 3 was prove something for n is equal to k plus 1. However, over here, we want to prove it for any integer n. Therefore, in step 3, we say the following. Prove this for n is equal to k plus minus 1, which means the following. We start with n is equal to 0. From 0, we can go in both directions. Basically, not necessarily from 0. As I said, in step 1, we can check for n is equal to, say, 1. It doesn't matter. We will go from 1 in both directions, positive or negative direction. Or we can put instead of 0, 2 or negative 2020. It does not matter. We will go in both directions anyways. So, keeping this in mind, we want to prove that 3 divides this. We replace n by k plus minus 1. If you don't like this, think about the following. Imagine that instead of example 9, we have 2 questions. Question 1, prove that this is true for n greater or equal to 0. And then example 2, prove that this is true for n lesser or equal to 0. These are 2 separate problems. In these 2 problems, step 1 will be absolutely same. We will start with n is equal to 0. In these 2 problems, step 2 will be absolutely same. Step 3 will be different. In problem number 1, n will be equal to k plus 1. Because in problem number 1, we want to prove that 3 divides this for any integer n greater or equal to 0. In problem number 2, n will be equal to k minus 1. Because in problem number 2, we want to prove that 3 divides n cubed minus n for any integer n lesser or equal to 0. We have to go in the negative direction. And now let us combine these 2 cases together. We want to prove that 3 divides n cubed minus n for any integer n. N is equal to k plus or minus 1. We want to prove that 3 divides this. By algebra, k, let me consider these 2 cases separately. If instead of plus minus, in both cases, we have plus, if we have plus here and plus here, k plus 1 cube is k cube plus 3k square plus 3k plus 1. Once again, if here plus, after we expand parentheses, we get minus. Now, to the contrast, if instead of plus minus, we have here minus and here minus, after we expand parentheses here, this minus becomes plus. If instead of plus minus here, we have just minus, over here, we still have plus. But over here and over here, we have minuses. And now let us put these two cases together. If here plus minus, here plus minus, we put here plus minus, but here minus plus. Means if here plus, plus plus minus. If here minus, minus minus plus. Lastly, let us group together k cube and minus k. Done. Let us cancel out 1 because plus minus 1 minus plus 1 is 0. And lastly, let us group together this and this. Done. This expression is divisible by 3 because if we factor out 3, it is of the form 3 times integer. This expression is divisible by 3 by step 2. Since this is divisible by 3 and this is divisible by 3, the whole thing is divisible by 3. Done. Any questions here?
Can you explain again what the difference between plus minus and minus plus is?
Very good question. Plus minus and minus plus means the following. If instead of plus minus here and here we have plus, then this plus minus becomes plus. This plus minus becomes plus. This minus plus becomes minus. Similarly, if instead of plus minus here and here we have minus, this plus minus becomes minus, this plus minus becomes minus, but this minus plus becomes plus. Does this answer your question?
Yes, thank you.
Other questions?
I'm still a little confused about the plus minus and minus plus.
Okay, so think about 2 separate problems. Imagine that we have the following question. Prove that this is true for any integer n greater or equal to 0. In this case, instead of plus minus here, here, and here, we will have plus. You agree with me?
Yes.
Okay. Therefore, here plus and plus. Therefore, here plus, plus, but here minus. Agree?
Oh, so
because when we expand parentheses, this plus becomes minus. Now, in the second case, suppose that we want to prove this for any integer n lesser or equal to 0. Then, instead of plus minus, we will have minus. But if here minus and here minus, this is minus, but this is plus.
So are you showing like the top sign is what it would happen in one case and the bottom is what would happen with the second case?
This is exactly what I said. Plus minus means in case 1, we have plus, in case 2, we have minus. Minus plus means in case 1, we have minus, in case 2, we have plus.
Okay, thank you. I understand now.
And note that no matter we have problem number 1 or problem number 2, 1 will be cancelled anyways, Because in problem number 2, here we have +1, but here -1. In problem number 2, here we have -1, but here +1. Now, example number 10 is very similar to example number 9. We just replace 3 here and here by 5. Step 1 is very similar. For n is equal to 0, this is true because 5 divides this. Step 2, we replace n by k. Step 3, prove that this is true for n is equal to k plus -1, namely this. And now the general idea is fundamentally same. We expand parentheses here and expand parentheses here. One can check that if we expand parentheses here, we get this. And now, as before, we cancel out 1. We group together this and this, which is divisible by 5 by step 2. And this expression is also divisible by 5 because we can factor out 5. Similarly here, computations are even more complicated, but the basic, the most fundamental idea is same. Now, guys, later in this course, we will prove the following general result. Suppose P is a prime number. P divides n to p's power minus n. Note that if we apply mathematical induction, it will be significantly harder to prove this general result, because we'll have to expand parentheses in the following expression, k plus -1 to the power p, and then we'll have to prove that if this is a prime number, each coefficient is divisible by p, which is not that simple. So it's another example when mathematical induction cannot be used as easily as in these examples. Folks, any questions here?
I just have a question about the notation. The little asterisk, what is it holding?
Means this. Let us denote this by asterisk.
Thank you.
Next, let us prove that 3 divides n cubed minus 7n plus 3. Again, as before, for n is equal to 0, this is true because 3 divides 3. Suppose this is true for n is equal to k. Suppose this. Prove that 3 divides this for n is equal to k plus -1. So we replace n here and here by k plus -1. Done. We copy this expression here. We expand parentheses. Done. We expand parentheses. Done. Since here minus plus minus becomes minus plus. And now let us do the following. Let us group together k cubed, -7k, and 3. Done. And then plus minus 1 minus plus 7 is minus plus 6. 3k squared plus 3k minus plus 6 is divisible by 3. This is divisible by 3 by step 2. Therefore, the whole thing is divisible by 3. Done. Next. Last type of examples. Now we are talking about inequalities. We want to prove that 2 to nth power is greater than n for any integer n. We can apply math induction in several different ways. Here's one possibility. Note that this is true for any negative n. Indeed, observe that no matter what is n, 2 to nth power is always positive. Think about the graph of an exponential function. The graph of an exponential function is always above the x-axis. So, no matter what is n, the left-hand side is positive. Therefore, if n is negative, the right-hand side is negative. Positive is greater than negative. So, this is indeed true for any negative n. We do not have to use induction anymore to prove that this is true for any negative n. Now, suppose n is non-negative. Suppose n is greater or equal to 0. We will use induction in order to prove that this is true for n greater or equal to 0. For the first time, we have to show that this is true for two values of n. For n is equal to 0 and n is equal to 1. This will be explained in a moment. We will understand it when we discuss step 3. So, suppose n is equal to 0. Our left-hand side is 2 to 0 power, which is 1. Our right-hand side is 0. 1 is indeed greater than 0. For n is equal to 1, our left-hand side is 2 to first power. Our right-hand side is 1. 2 to first power is 2. 2 is greater than 1. Step 2. Suppose this is true for some integer n is equal to k, which is greater or equal to 1. Note that in all previous examples, if here we have some number, here we have same number. However, since in step 1 we showed that this is true for n is equal to 0 and n is equal to 1, here we can put 1. Suppose this is true for some integer n is equal to k, which is greater or equal to 1. That is this. Now, let us prove that this is true for n is equal to k plus 1. Namely, this. Here's how we do it. Let us start from the left-hand side. Note that 2 to the power k plus 1 is 2 times 2 to k. By step 2, this is greater than this. Here is why. Please take a look at step 2. If you multiply the left-hand side here and the right-hand side here by 2, on the left-hand side, you will get 2 times 2 to k's power. On the right-hand side, you'll get 2k. It's exactly what is written here. So, in order to obtain this, just multiply both sides by 2. Lastly, remember, in step 3, we want to prove that this, which is over here, is greater than this. Right now, we know that this is greater than 2k. Therefore, what is left is to show that 2k is greater or equal to the right-hand side, k plus 1. So we still put here question mark. Why 2k is greater or equal to k plus 1? Because if you subtract k from the left-hand side and from the right-hand side, on the left-hand side, you will get k. On the right-hand side, you will get 1. You will get this. Is k greater or equal to 1? Yes, it's written over here. This is why in step 1, we need n is equal to 0 and n is equal to 1. Indeed, if in step 1, we show that this is true for n is equal to 0 only, in step 2, we'll have to put 0 here. Therefore, in step 3, we will not be able to prove this, because this can be rewritten as this, and if here 0, this is simply not true. If k is greater or equal to 0, this does not mean that k is greater or equal to 1. Therefore, if here 0, we will not be able to prove this. Lastly, this proof can be made shorter if we replace this word negative by the word non-positive. Indeed, if sentence number 1 is the following, note that asterisk is true for any non-positive n, then in step 1, we can check that this is true for n is equal to 1. Because if instead of negative, we have non-positive, the opposite case is n is greater or equal to 1. But if over here n is greater or equal to 1, in step 1, we'll have to check only for n is equal to 1. So if instead of the word negative, we have the word non-positive, here we put 1. Therefore, there is no need for this portion. And our proof is a little bit shorter. All right, let us discuss other examples. Prove that 2 to nth power is lesser than n factorial for any integer n greater or equal to 4. Step 1, show that this is true for the lowest possible n, which is 4. You replace n by 4 here and here. The left-hand side is 2 to 4th power, which is 16. 4 factorial. 4 factorial is 1 times 2 times 3 times 4, which is 24. True. Step 2. Suppose this is true for some integer n is equal to k, which is greater or equal to 4. Namely this. Step 3. Prove, here question mark, prove that this is true for n is equal to k plus 1. Prove this. As before, we start from the left-hand side. Here is the left-hand side. 2 to k plus 1 can be rewritten as 2 times 2 to k's power. By step 2, this is lesser than this. Here is why. Just multiply both sides by 2. Indeed, we will get this. So, by step 2, 2 to k plus 1 is lesser than 2 times k factorial. But we want to prove that 2 to k plus 1 is lesser than k plus 1 factorial. So, in order to prove this, what is left is to show that 2 times k factorial is lesser than k plus 1 factorial. Copy this here. Observe that k plus 1 factorial is k factorial times k plus 1. Here is why. K plus 1 factorial is the product of all integers from 1 to k plus 1. Note that the product of all integers from 1 to k plus 1 can be rewritten in the following way. The product of all integers from 1 to k times k plus 1. But the product of all integers from 1 to k is k factorial times k plus 1. Lastly, we cancel out k factorial, done. We subtract 1 from both sides, we get the following. K is greater than 1. This is true because k is greater or equal to 4. So question mark here is gone. Lastly, this implies this, which implies this, which implies this. Any questions here?
Can you go back to step 3 and
Yes.
like explain I guess how you replaced in step 2?
Yes, absolutely. So 2 to the power k plus 1 is 2 times 2 to k. You agree?
Yes.
Now, please take a look at this inequality. Multiply both sides of this inequality by 2. If we multiply both sides of this inequality by 2, the left-hand side becomes 2 times 2 to k's power. It's exactly what is written here, correct?
Yes.
Right-hand side becomes 2 times k factorial. It's exactly what is written here. So if you multiply both sides of this inequality by 2, you will get this. Does this answer your question?
Yes, thank you.
Example 15. We want to prove this for any integer n greater or equal to 1. For n is equal to 1, this is true because 1 factorial, which is 1, is equal to 1 to first power, which is 1. Suppose this is true for some integer n is equal to k, where k is greater or equal to 1. Suppose k factorial is lesser or equal to k's power. We want to prove that this is true for n is equal to k plus 1. Namely this. Here we have question mark. Let us start from the left-hand side. Here is the left-hand side. As we discussed before, remember I said here that k plus 1 factorial is k factorial times k plus 1. K plus 1 factorial is k factorial times k plus 1. Now, if we multiply both sides of step 2 inequality by k plus 1, the left-hand side becomes this, the right-hand side becomes this. So this is lesser or equal to this by step 2. Lastly, let us show that this in turn is lesser or equal to k plus 1 to k plus 1 because we want to prove this inequality. Why this is lesser or equal to k plus 1 to k plus 1? Because if you cancel out k plus 1, on the left-hand side, k plus 1 will be gone. So what is left is just k to k's power. If you cancel out k plus 1 to k plus 1 becomes k plus 1 to k, which is exactly what is written here. But of course, this is lesser than this because k is lesser than k plus 1. Done. Example 16. Prove that 3 to n's power is lesser than n factorial. Guys, basically, if you compare example 14 and example 16, here's what we're trying to say. N factorial is growing faster than 2 to n's power. N factorial is growing faster even than 3 to n's power. one can show that no matter which integer we put here, n factorial will be greater than a to nth power starting from some number. Here, n factorial is greater than 2 to nth power starting from 4. Here, n factorial greater than 3 to nth power starting from 7. Basic idea is same. We show that this is true for n is equal to 7. Suppose this is true for n is equal to k, where k is greater or equal to 7. Suppose this, or we want to prove this. We just replace n by k plus 1. And as before, we start from the left-hand side, done. 3 to k plus 1 is 3 times 3 to k's power. If we multiply the left-hand side and the right-hand side by 3, we will get this. So, by step 2, the left-hand side is lesser than the right-hand side. By step 2, 3 to k plus 1, which is over here, is lesser than 3 times k factorial. But what we need is to show that 3 to k plus 1 is lesser than k plus 1 factorial. What do we do? What is left is to show that 3 times k factorial is lesser than k plus 1 factorial. And as before, in order to prove this, which is over here, rewrite k plus 1 factorial as k factorial times k plus 1, cancel out k factorial, done, and then subtract 1 from both sides. K is greater than 2. Since k is greater or equal to 7, of course, k is greater than 2.